Hello, everyone. My name is Colton Willits. I am a student at Dakota State University, currently in the INFA-735 Offensive Security course. I will be presenting my research on neutralizing the anti-malware scan interface via live memory patching on Windows 11. So what I'll be covering in this presentation is what exactly AMSI is, why attackers target it, known AMSI bypass techniques, proof of concept memory patch that I actually worked on, the lab environment, and the actual execution portion of that proof of concept patch, an example demonstration, my results, and the impact and conclusion of my research. So what is AMSI? So as I stated originally, AMSI is the anti-malware scan interface. It was actually introduced with Windows 10, and the whole purpose of it is to actually be able to scan input that goes into PowerShell, command line, anything like that in Windows, and will kind of send that over to Microsoft Defender to analyze it and determine whether or not it can be considered malicious code. How AMSI works is essentially you have to think of it as an API with the Windows Defender service. So if you look at the diagram, you can see where you have PowerShell, Visual Basic Script, anything like that, and that will interact with that AMSI layer, that API layer, which then actually will reach back to the Windows Defender service engine. And then that is actually what makes the determination on whether or not something is malicious or not. And then it will send that back to whatever process is actually reaching out to AMSI. So some of the weaknesses that actually are included with this, AMSI runs in process with whatever you're running, right? So you pull up a PowerShell prompt, and essentially in that prompt, when you go to run something, it also will run AMSI with it. So they're both loaded into memory at the same time. It's not a security boundary per se, more is less kind of like an extra defense in depth measure on running fileless malware or malicious code. And you can actually, because it is in memory, modify the AMSI code that is there. You're able to directly overwrite that. And that makes this attack vector actually very feasible for evading antivirus. So some of the known techniques is being able to flip the AMSI init failed via a .NET reflection, being able to overwrite function pointers, doing a patchless bypass just by using exceptions. And then kind of what we focused on in this was Rasta Mouse's memory patching technique, which you are targeting the AMSI scan buffer. So you're trying to overwrite that and then force it to return out of the program running in memory. So for my goals with this, what I was trying to do was essentially be able to work on all Windows 11 supported architectures, whether it be ARM64, x86, x64, right? And kind of have something that's a universal tool that can be used across all Windows platforms. Another goal was to have it actually work on the latest version of Windows. So whatever defense mitigations that Microsoft has implemented on the latest patched Windows, to be able to actually evade that. And then use a proper detection benchmark. And in this case, what we ended up using was Mimikatz, to have something that can be flagged by Windows Defender, while at the same time as giving me a good basis of like, hey, if I can get this to run, then it shows that our proof of concept worked. So for the lab environment, I'm running this on a Apple M1 Mac Mini, which is an ARM64 based architecture, using Parallels as my hypervisor. running Windows 11 ARM64, and then our attacker machine is going to be a Kali Linux box that is also ARM64. One notable mention is the PowerShell 7 portion. Just due to the way I ended up getting the .NET package and building it, I built it in a way that it only works on PowerShell 7. Had I compiled it with a different .NET version that supported just basic PowerShell, that would have alleviated that issue, and I could just run it based off of the native PowerShell function that's on Windows itself. But we ended up having to install PowerShell 7 just due to the .NET compatibility issue. And then, of course, having Defender fully enabled, except for automatic submissions in this case, just because it was something I didn't want to have sent to them. And next thing you know, I go to test it and it doesn't work. So let's talk about Microsoft's new detections that we discovered while we were working on this. So Microsoft Defender, if you look at Rostam Mouse's architecture in his code, what he is doing is actually calling out AMSI.dll and AMSI scan buffer. These are actual things that Defender will now flag when you try to load in a DLL. If it recognizes those strings, it will flag it as malicious, and then it will also block anything that's calling a load library or a get process with those same strings as well. So we ended up just being able to evade that portion just by simple obfuscation. We broke the strings into fragments and then reconstructed them via ASCII character arrays. We used base64 encoding to kind of just obfuscate as much as we could. And then even renamed our DLL to something that would be considered non-suspicious, just trying to bypass some of these flags that Microsoft Defender was throwing on my initial code. So how exactly does the patch work? So essentially, we're going to be initially loading the AMSI DLL, and then we're going to be locating the AMSI scan buffer within memory. We will then be changing the memory protections on that memory address. Then we'll just write the architecture-specific patch code to that memory, so it overwrites it, and then we restore memory protections, just so that it kind of closes everything up and makes it look like it still has integrity. So for the patch logic, written in obfuscated architecture-specific assembly. So if you look at the two images on the side, you will see the code in C that actually has that assembly obfuscated in there. So on the top, you'll see x64, and then below that, there's just a string that just falls back to an x86 patch byte. These are just based off of Rostam Mouse's exact patch code, right? It's the same thing, just obfuscated a bit to kind of defeat the antivirus. And then, of course, with our system, because we ended up having to test this on ARM64 since it's the only architecture I had for this, we just ended up writing in an ARM64 assembly a return instruction that gets written into memory. So for this live demo, we're going to be kind of looking at the setup and configuration overview of what Windows version I'm using, how up to date it is, how I kind of staged out the server to be able to pull it off as fileless. I'll be showing you that AMSI will actually block Mimikatz normally, and then I'll show you that actual memory patch applied with our proof of concept, and then AMSI being completely disabled afterwards to the point of we can even run that initial test file that we use to show that Mimikatz is blocked. And as a disclaimer, this demonstration is for educational purposes only. I am not responsible for whatever you do with this information. So yeah, let's get into the demo. All right. So for our Windows 11 machine, we're running Windows 11 Pro with 25H2 build 26200.7171. I actually went and updated this beforehand just to make sure that we had the latest Windows Defender definitions, the latest cumulative updates, so on and so forth. Okay, so for our attacker machine, we're just running Kali Linux. So we'll see here, I have this set up in a few different ways. You can see on the Explorer side where I have the actual .NET project with the code here. And then I have this www directory, which is actually being hosted on just a simple Python HTTP server, right? So to cover this exact exploit, or I should say antivirus evasion technique, with this DLL that's being written here, this automatically gets named to system.updater.service.dll is what we're going to be pulling. But initially, what we have to do is we have to load in the kernel 32 API to call in a different process each time, right? So we're going to be using one API call for load library. We're going to be using another for getting the process address. And then we're going to be loading another API call for virtual protect, which is for memory protection. Getting into the main function, we can see the string that is being used. So this just spells out AMSI DLL, just obfuscated. For the function, it's just AMSI scan buffer, also obfuscated. And then what we're going to be doing is we're going to be passing that DLL in the load library. So it's loading the AMSI DLL. And then this is just a safety feature. If it fails to load, just return out. And then what we're going to do is we're going to get the memory address of AMSI scan buffer after it's been loaded into memory. So what this allows us to do is essentially be able to have the pointer to where the AMSI scan buffer is within memory. From there, what we're going to do is we're just going to go get that patch, right? So we'll come down here to the get patch function, and this will go through, check the system architecture and see if it's ARM64 or x64. Otherwise, it will just fall back on x86, right? And it will return this little bit of assembly here back up to this byte array. After that, we will essentially be changing the memory protections on the AMSI scan buffer address, so that way we can write to it. and then we will just loop through each byte within the byte array and essentially write that to memory, and then we're closing it out, right? We're just returning that memory protection back on for that address, and that's about it for the actual evasion technique with the DLL. However, it takes a little bit more to actually get it to work. So in here, so what we did to make it easier with obfuscation is we actually just took the compiled DLL and changed it into a base 64 encoded string. Essentially, it's just a really big long string that we have here. And what that will be used for is that will actually be used for loading the DLL. And then this invoke mimikatz PowerShell script, which we get from PowerSploit within Kali Linux, is really only for like x64, x86 systems. So it will throw errors because we are running it on ARM64. However, it still shows us that it's able to bypass it effectively without running mimikatz. So we have two different ways we went about this. So we had a test file, which initially all this does is it pulls that invoke mimikatz script, which is base64 encoded into the second stage. And then what it will do is it will take the content of that and read it out and convert it from base64. And then it will run the invoke mimikatz command, which is base64 encoded as well. And then it will just pause so it doesn't exit and we can actually see it, see its output. And this is just what we're using to test, see how Windows Defender will respond to this. Now, for a proof of concept, what we're doing is we're pulling in that obfuscated DLL, which is also in base64, so it's just reading that out. Then it will actually load it, and then it will wait. So it's going to wait 500 milliseconds to actually allow it to take effect within the system. And then after that, we're just going to be pulling over that invoke mimikatz PowerShell script, loading that into memory and calling it with that invoke mimikatz command that is also base64 encoded. And then, of course, the pause we got here, the little manual pause. So what we'll go do here is I will come back over to Windows, and we're going to look at our Windows security settings. So it's going to chew me out here because I changed it already. But we'll just come in here, take a look. Ransomware protection is still on. Virus and threat protection updates have been updated to the latest versions. Currently detects no threats. And then, hang on. That one. Okay, so in virus and threat protection settings, we have real-time protection on, dev drive protection on, cloud delivery protection on. We disabled automatic sample submission, so it doesn't submit our mimikatz. And then tamper protection is also still turned on. So Windows Defender is still completely enabled. So in PowerShell here, we're just running a command to actually just pull over that PS1 and load it and run it. So let's start with that. Hang on. I tested it beforehand, and that's why it did that. So we'll come back in a new PowerShell session and run the test file. And what it's going to do is it's going to say, hey, this contains malicious content, and it's flagging both the script as well as the command that we're trying to run. So now what we'll do is we will run the proof of concept, and you can see all of this output here as Mimikatz. The Mimikatz PowerShell script is not compatible with ARM, so it's sitting here complaining a lot about it. But there is no flag for anything malicious within this. It's just yelling about the Mimikatz itself. And to just kind of show that within this session, we can still continue to use it. Once it's been attached to this session, it will still use that same code within memory, even though we overwrote it. We will just run the test file again, which won't flag, and you just get the, hey, my Mimikatz is broken just due to the architecture. But that is the demo. So for our results, right, we saw that the AMSI bypass was able to succeed across the latest version of Windows 11 25H2. Initially, when I tested this, I started with 23H2 and continued updating it. However, I can't really roll my virtual machine backwards in this case, and repeatedly do this across all versions of 23H2, 24H2, and 25H2. So we went with the latest version. We saw that the memory patch persisted until the session actually closed. This really just highlights, Microsoft's mitigation of trying to detect strings or signatures based off of strings that are within the code. Doesn't truly mitigate that when it can be defeated with simple obfuscation, right? And then of course our Mimikatz actually never triggered detection after we ran that patch either. So the security impact of what this looks like. So on the CVSS version 3.1 scale, we're looking at about a 6.3, which is about a medium. This is mainly due to the fact that the attack requires local code execution, so you have to have a user count or some sort of user access onto the system where you are able to run PowerShell or command line or something of that sort. This technique is relevant in post-exploitation scenarios. However, it's not something that can actually gain you any sort of information. But however, it does directly impact the integrity of AMSI in memory and how it interacts within Windows. And then, of course, indirect impacts, right? Confidentiality, right? It's removing some of the protections to sensitive data, credentials, et cetera, like the SAM file, different things like that, because it's allowing you to use things like Mimikatz or any other tools that would normally be flagged on Windows to run and actually execute on the system. And then integrity, of course, it removes the protection to modify system state. So you would be able to use it to kind of manipulate or tamper with the OS. So for our conclusion, pretty much AMSI, even though it's a great protection, great concept for handling fileless malware, it's really not that robust when it comes to simple bypass techniques like memory patching, right? It's still vulnerable on the latest and greatest Windows versions, and Microsoft is just relying on string signatures and not actually fixing the architecture of how AMSI integrates within Windows. And then, of course, essentially, defense in depth is going to be your most essential point in this. So when it comes to defense in depth, layering your security controls, layering different things like hardening your firewall, hardening your host, making sure that your antivirus is up to date. If you have an intrusion detection system of some sort, whether it be endpoint based, just actually layering in those different controls to actually be able to mitigate the potential of coming to this point. But that is all I have for this. So references, but thank you for watching.